Welcome to this lecture. The main part of the lecture will be a proof, a quite lengthy proof, and I'm going to show you the following. So what we have seen in the previous lecture is that we consider the LTL model check-in problem, which is given a finite transition system and an LTL formula, we would like to check whether the transition system satisfies the formula or not. Yeah, so we're interested in this question: does T satisfy phi? The construction I explained to you in the previous lecture quite extensively is that the idea is to transform actually the negation of the formula, because we are interested in refuting the property. So we take the negation of the formula and we're going to construct algorithmically a non-deterministic Büchje automaton for this formula. So how does this work? The key idea that I explained last time was to take the formula and build certain subsets of its subformulas. And we called that the closure. So I briefly recap this here. So what we are going to do is we take a formula, and the last time we had a formula like this. If this is the input formula, what we're going to do is we look at all its subformulas. So things like A, things like next A, things like A and next A, the whole formula, etc., plus their negations. So we also look at not A, we look at not next A, we look at not A and next A, and we look at not phi, etc. Yeah? And we call this the closure of phi. And now the key idea is that the states of the automaton are provided by taking certain subsets of this set. Then the question is, which subsets are we allowed to pick? And they are what we call the elementary sets. So just briefly, we take a subset of these subformulas, and we call it elementary, and there are basically two conditions. The first one says it's maximal consistent with respect to propositional logic. That means the following: if a formula psi is in the closure, then the first rule says if you did not select psi, then you should select its negation. No? The second rule says if you have a conjunction in the closure and you have selected, you can only select this conjunction if and only if you have selected both conjuncts. And please bear in mind, it's an if and only if, so it means that if you select psi1 and you select psi2, this is an obligation to also select the conjunction. Otherwise, the set is not elementary because you don't fulfill this condition. And the third line says, okay, if there is a subformula true in the closure, then it's your obligation. You should always select this subformula. Intuition being this subformula is always true. The set B will become a possible state in my automaton, and that simply means that this state satisfies true. The second condition is about the until, and that says the following should hold. If there is an until formula in the closure, like in my case the whole formula, then there are two conditions you need to check. If the until formula has been selected, but the right-hand side of the until, psi2, has not been selected, then there is only one possibility to make the until formula true somewhere in the future, namely that this, but the current state satisfies psi1. So you should select psi1 there. So this is, again, an obligation. And the second one says if you have selected psi2, then it means actually that this until formula is vacuously true, and that says this, then the obligation is that you should also include the until formula into the set B. Okay? So this gives rise to several subsets, and actually in the previous lecture we saw that we get something like B0, B1, I think up to B4. So we get something in this example 5 sets satisfying all these constraints. Good. The key idea is those sets are the states. So what's now the GNBA? The GNBA has a state space, all those subsets, B's, that are elementary, that satisfy all the constraints we have just seen. The initial state is are those states that actually include the original formula phi. And then there is a transition relation that says the following: give me a state B, and we're going to look at the transition relation with respect to some set of atomic propositions A. Yeah? Because the transitions are labeled with sets of atomic propositions or logical formulas. And this says, okay, if A differs from the set of atomic propositions in the current state, then there is no outgoing transition from B with the symbol A. If, however, A is exactly the set of atomic propositions in the current state B, then the next state, or the set, I should say, of next states of state B with respect to the input symbol A is a set of possible successor states. And these successor states have to satisfy two constraints. The following: if the current state includes something of the form next something, this must be true if and only if this something, psi, belongs to the next state B prime. Yeah? Notice that B prime is the state that I'm moving to. So the next line says, okay, if you have an until formula in your current state, then either psi2 is already true in the current state, and then there is no obligation on B prime, or psi1 is in the current state, but then there is an obligation on the successor, because that means that then the until formula is not already true in B, and there is only one possibility to establish its truth, namely that the successor state satisfies or is labeled or contains the until formula. Good. Finally, we have actually a GNBA, so we make the construction by first going to a generalized Büchi automaton. This means that we don't have a single set of accept sets, but a set of sets. And the intuition is that for every until subformula, we have a set. So we look at the closure of the original formula, we look at an until formula, and for every such until formula, there is an accept set. That's what this definition says. Okay. How is this F for one until formula defined? This is defined as follows. So one set of states for this until formula in the closure is defined as a set of states in the automaton such that the until formula is not in that state, or the right-hand side, psi2, is in that state. Okay? Now, this is the definition of the GNBA, and what I would like to show now is why is this correct? Yeah. And so what we're going to do is we're going to go through the proof step by step to show why this is correct. So what I want to show is the following theorem, and this is basically the correctness of the LTL to GNBA construction. And this says the following: for every LTL formula phi and GNBA G of phi, which is the one I just defined on this slide, it holds that the set of infinite words accepted by this automaton is exactly the words of phi. So what does this mean? This means the set of infinite words accepted by G phi equals the set of traces satisfying phi. Good. This is what we want to show. Good. So how are we going to do this? This is an equality, so we're going to prove subset inclusion in both directions. So part one. I'm going to first start with this subset inclusion. So how are we going to prove this? Well, we pick something in the set words of phi, And we're going to assume let sigma is something of the form A0, A1, etc., such that A of I is a subset of the closure of phi. That means sigma can be written as B0 intersection AP, B1 intersection AP, B2 intersection AP, etc. This is the sigma we have at our disposal, such that AI intersected with the closure of phi equals BI intersected with AP. Good. So we have that BI is the following set. These are all subformulas of the closure of phi, such that the sequence starting at that position, so here is an I, there is an I, of all A's, this satisfies the formula psi. No, phi. Yeah. Phi. That's good. Good. This is what we should keep in mind because that's what we're going to use quite a bit. Good. Now what we're going to prove, we will prove that the sequence of B's, so B0, B1, B2, is a run of the automaton G of phi. That's the first thing I'm going to prove. Later I'm going to prove it's also accepting. I'm first going to show the sequence of B's is a run. Good. And it's a run for the input word sigma. Good. First, observe that B0 is an initial state of G phi, since by star, which is the thing here in the box, B0 are all formulas in the closure such that A0 satisfies phi, right? So that means that phi belongs to B0. And we know by definition that all the states that include phi are initial states. So slowly, what do we have? We have that by star B0 is the set of in the closure such that A0, A1, etc. satisfies phi. Yeah. This is true, yeah, since sigma belongs to the words of phi. And this A0, etc. was sigma. Good. So B0 is an initial state. That's what we know. What else do we have to know? We have to prove something about the successor relation because we want to prove it's a run. The only thing we know now is that this run starts in the initial state. That's good to know. But now what we have to prove is the following. So now we have to show also we have that Bi plus 1 belongs to delta Bi of Ai. So this tells you that Bi plus 1 is a successor of Bi if you take as next input symbol Ai. Why Ai? Yeah, because that's what sigma is, right? Sigma is the sequence of A's. Since the following things hold, Ai equals BI intersected with AP. Look at this slide. This is important because otherwise there is no successor. So we have to be sure that we are in this case, which is the case by construction. B. If you have a next formula, so now what do I need to check? I need to check these two conditions. Yeah? So how do I get these conditions? Assume that next psi belongs to the closure of phi. For that it holds the following. Next psi belongs to BI if and only if, by condition star, that AI plus 1 satisfies next psi. But this means if and only if AI plus 1, AI plus 2 satisfies psi. Now, here I just use star, here I use the if and only if, and I'm a little bit confused because sorry, I made one typo which I see now that is a typo. This really must be a psi. So this argument still holds. We take all the psi satisfying psi, but we know that sigma satisfies phi, and therefore it follows that phi belongs to B0, and therefore it follows that B0 is initial. But now I saw that here I need this psi. So next psi belongs to BI. Look at star. That means that AI plus 1 satisfies this formula, which is next psi. Now you apply the semantics of LTL. If this sequence satisfies next psi, then the sequence from the next position on needs to satisfy psi. But that is true, again by star, if and only if psi belongs to BI plus 1. Yeah? If this satisfies psi, by definition of star, psi belongs to BI plus 1. And here you have exactly the first rule. Next psi belongs to the current state if and only if psi belongs to the next state. Sorry for the cameraman, I'm moving a bit today. Good. So what else? We need also to prove C, namely for an until formula. So we show that if you give me an until formula in the closure of phi, we have the following. Phi 1 until phi 2 belongs to BI. Yeah. Notice where I am. I am here on the left-hand side of this if and only if. Now I have to prove the right-hand side. So this means if and only if, again by construction, so by star, it follows that AI plus 1 satisfies phi 1 until phi 2. But this is true, as you all know. That means that either AI plus 1 satisfies phi 2. So here I use expansion law. Yeah. I was already hinting at the point that the expansion law is crucial in this algorithm, and here is where one of the places where we use it. This means that AI plus 1 satisfies phi 2, or AI plus 1 satisfies phi 1, but then also the next thing, the next state, so starting from ai plus 1, ai plus 2, it needs to satisfy phi 1 until phi 2. Good, but this holds again by star. That means that this is from I on, so that means that phi 2 belongs to bi, or phi 1 belongs to bi, and this end, phi 1 until phi 2 belongs to bi plus 1. Yeah. This is the same as saying ai should satisfy next, and therefore I've shifted this index by 1. Thus, altogether, B0 is an initial state, and we have that bi plus 1 belongs to delta bi ai. So B0, B1, etc. is a run of G phi. Good. What is left? We need to prove it's accepting. Yeah. So now it comes, why is this acceptance condition really the acceptance condition we need? So the second part of the proof, 2. So the only thing we know is a run. Now I want to show that B0, B1, etc. is accepting. Good. Let the set of accept states be something of the form F1 up to Fk. Yeah, so these are the accept states, the accept sets of my automaton. Good. To prove bi, some index in the run, needs to be in f of j, yeah, for all j, for infinitely many I. No, I mean the intuition is here we have B0, B1, B2, etc. B27, B100, etc. Now we have to fulfill all the accept conditions, so pick one. I take Fj. What do I need to prove? I need to prove that this run visits Fj infinitely often. What does that mean? There are infinitely many indices, let's call them I, such that I visit some state in Fj. Yeah. So I is an index here. Yeah, maybe this belongs to Fj. Maybe this is another I that belongs to Fj. And what I need to prove? I need to prove that there are infinitely many of those I's. Good. Let Fj correspond to a certain subformula. Why do I know this? Well, I know that all those f's, f1 up to fk, are induced because they belong to a certain until subformula that belongs in the closure. So number j, let's say it corresponds to the formula phi 1j until phi 2j, which is an element of the closure of phi. Now we're going to show this by contraposition. That means I'm going to work towards a contradiction. So how do I get to a contradiction? We're going to assume that bi belongs to fj for finitely many. Yeah, I need to prove it for infinitely many. Now I'm going to say it's for finitely many. And then let's see whether we can get a contradiction. Good, let's call this condition triangle. Good, it holds that if bi does not belong to fj, implies that this subformula belongs to bi, and the formula phi 2j does not belong to bi. Yeah. An element does not belong to this set if the negation of this part is true. The negation of the part means this part is in the set and this thing is not in the set. Yeah? It's just a negation of what is written down on this slide. So this holds by definition of fj. Good. As bi is what? Well, that was the definition, closure of phi such that ai plus 1 satisfies psi. Yeah. This was my star before on that board over there. It follows bi does not belong to fj implies, yeah, now I can show you this. I can basically write this down as follows: ai plus 1, etc. satisfies phi 1j until phi 2j. So what I do is I replace this bi by this ai, etc. satisfying the formula, which I can do because of this definition. And I do the same for the second part. And this is not in bi, which means actually that the sequence ai plus 1, etc. violates phi 2j. Good. From star, from this, so let's call this, I don't know what, A. A is maybe bad, right? Let's call this small a, let's call this B. From A, what can I conclude from A? From A it follows, yeah, if this sequence satisfies this formula, it means there must be a k, ak plus 1, etc., satisfying the second part of the formula, phi 2j, for some k at least, well, I. No? If this sequence satisfies the until formula, it needs to be the case that, yeah, phi 2j should hold some point at some point k. Yeah? By 2, it says k differs from j, because this itself does not satisfy this formula. So, what do we know? K is larger than j, strictly larger than j. I, of course. Yeah, we're talking about at least I. This one says phi 2j is not satisfied by ai, so k is strictly larger than I. Sorry, not j. Good. Then phi 2j belongs to bk. No. For some k strictly larger than I because of this and because of the definition of bk. And by definition, bk belongs to fj. Yeah, because we have phi 2j, and because of the definition, if there is if the second part of the until formula is true at some position, then you also satisfy this thing. So what have we concluded? We conclude this from what? Where did we start? We started by saying bi belongs to fj. So summarizing, so from bi belonging to fj, we conclude bk in fj for some k strictly larger than I. And now I can repeat the argument for bk. Yeah? Here I start with I. Now I get that at some point later, I again have a state that is in fj. Now you can do the same reasoning starting with bk. You will get there exists some L strictly larger than k that again is in fj. But that means there are infinitely many, which contradicts my assumption that there are only finitely many. Yeah? So repeating this argument, so this simply means induction, right? To bk yields that there are infinitely many i's such that bi in fj. This is a contradiction to the formula which was in the triangle. Because the triangle said there are only finitely many. Good. This was one direction of the proof. Yeah. But I hope you see that the steps we are doing is quite elementary. And the reason I do the proof is that you also hopefully try to understand why this acceptance condition is the right acceptance condition. Yeah? And exactly that part of the proof here is, to my opinion, very important. Any questions so far? So what did we prove so far? We have shown that if sigma satisfies phi, then actually there is an accepting run in the automaton for this word. Now we're going to construct the other way around. We want to prove that this automaton does not accept more. Yeah? So that's the next step. Okay, so second part of the proof, we have to show the inclusion in this direction. Okay, so now I take a word which is accepted by the automaton. So this is something of the form A0, A1, etc. And this is accepted by my automaton, G of phi. To prove, sigma satisfies phi. My automaton does not accept anything that does not satisfy phi. That's basically what we need to prove. Good. What does this mean? That this means that, that G phi has an accepting run. Yeah, because otherwise this word would not be in the language. Let's say this was an accepting run B0, B1, B2, etc., which is an accepting run for sigma. Good. Since delta bi ai is empty set if AI differs from BI intersected with AP, it follows, quite similar to what we have seen before, that AI actually equals BI intersected with AP. Otherwise, this B0, etc., could not be an accepting run for this trace. Good, and this holds for all I, right? Thus, what we know now is that sigma is of the form B0 AP, B1 intersected with AP, etc. This is what we know about the shape of our run. Good. We proved now the following claim, and this claim is a little bit more general than the one that we have to prove, but this turns out to be fine. We proved the following. For all psi in the closure of phi, and B0, B1, etc. being an infinite run, so this is under Q omega, and we have such a sequence A's, A0, A1, etc. belongs to 2AP omega. And I, BI plus 1 is a successor of BI and AI for all I. And there are infinitely many i's such that BI belongs to Fj for all Fj in this set of accepting states, set of sets of accepting states, then, so if all this together holds, right, then psi belongs to B0 if and only if A0, A1, A2 satisfies psi. Why is this of interest to us now? Well, we need to show that sigma satisfies phi. So we need to show that this satisfies phi. So that means actually that if you interpret this as being sigma, if you take psi, what was psi? Well, psi is any formula in the closure, so including phi itself. Yeah? So that means that phi belongs to B0 if and only if this A0, etc. satisfies phi. This is what we want to prove. Yeah? And now what this claim is going to tell you, in order to prove this, it suffices to prove this, because this is equivalent to this. Yeah, so interpret this as follows. Maybe I write it down to make this clear. So our obligation is sigma satisfies phi. This is of the form A0, etc. satisfies phi. Yeah. Provided we can prove the claim. So by the above claim, assuming all those conditions hold, it suffices to show that phi belongs to B0. Good. So now what we're going to do, we're going to focus to prove this, let's say, double star. Once we're done with this, we're basically actually done. How are we going to prove this claim? Yeah, so this is the This is proven by induction over psi. By induction on the structure of psi. Now I'm going to skip the base cases. I'm going to skip the trivial cases, negation, conjunction, etc. I'm going to skip next. I'm only doing the hardest part. So we only consider psi is of the form phi 1 until phi 2. So in particular, the induction hypothesis is that the claim holds for phi 1 and it also holds for phi 2. Yeah, that's what I'm also, of course, going to use in the proof. Good. So what do we need to prove? Well, we need to prove the claim, which is written then there. So to prove is the following. Phi 1 until phi 2 belongs to B0 if and only if A0, A1, A2 satisfies, well, this whole thing there, which is phi 1 until phi 2. This is what I need to prove. How are we going to prove this? In two parts. I need to prove this if and only if, which is an implication in both directions. So we first start with the implication from right to left. So assume A0, A1 satisfies phi 1 until phi 2. Good. What does that mean? Then we know that AK plus 1, etc. satisfies phi 2 for some k at least 0. And AI plus 1 satisfies phi 1 for all i's between 0 up to but excluding k. Semantics of until. Now you apply the induction hypothesis. To both phi 1 and phi 2. Yeah, because here I have something which is a part and this is a part, so now I can apply the induction hypothesis. And this gives me that phi 2 belongs to bk. Yeah, because this says if, if this holds for ak satisfying phi 2, then phi 2 must belong to bk. And yeah, we have that phi 1 belongs to bi for all i's. Now you can apply induction by induction on k. It follows that phi 1 until phi 2 belongs to bk, bk minus 1, etc. So recursion backward, induction backwards to b0. And this is what we needed to prove. We needed to prove that phi 1 until phi 2 belongs to b0. Yeah, because we started with this phi 1 until phi 2. From this bk, we know that now k is also satisfying phi 1 until phi 2, and then you apply the same argument again and again and again, and then you get this result. good, that was implication from right to left. What about implication from left to right? So the second part, which I call B, is now the implication from left to right. So now I take let phi1 until phi2 belongs to B0. So we know that B0 is elementary. As B0 is elementary. Why do we know this? Yeah, because all the B's are states in my Büchi automaton and all states are by definition elementary. But by using this elementary, I know that either phi1 belongs to B0 and interpret this as phi2 not being in B0 or phi2 belongs to B0. Two cases. Let's first take the case that phi2 belongs to B0. But that's easy, because then by induction hypothesis we have that A0, A1, etc. satisfies phi2, and this implies that A0, A1 satisfies phi1 until phi2, thus phi1 until phi2 belongs to B0. This is not important, this is nonsense, this is enough. This is what we need to prove. Second case, phi2 does not belong to B, 0. And problems are always in the last case, so here this is a bit difficult. Then it means that phi1 is in B0, and by definition phi1 until phi2 belongs to B0. Because this was already what we know. This says that phi1, so this is already what we go from here. Yeah, so this is what we know. Good. We prove that phi2 belongs to Bj for some j larger than 0. And this is done by contraposition. Assume phi2 does not belong to Bj for all j. From the definition of delta, I mean this delta over here, we obtain that phi1 belongs to Bj and phi1 until phi2 belongs to Bj for all j at least 0. This is by induction, by structural induction. Yeah, from this assumption. As B0, B1 satisfies all accept sets. Yeah, this B0 was an accepting run, so it sets all the accept sets. We know the following. We know that Bj belongs to F phi1 until phi2 for infinitely many j's. On the other hand, we have that phi2 does not belong to Bj. Where is this coming from? Well, that was here. That was our assumption. Yeah. And phi1 until phi2 belongs to Bj. If and only if Bj does not belong to f phi1 until phi2 for all j. This holds for all j. This is a contradiction. Yeah, because here I concluded Bj in F, this set for infinitely many, and this I said Bj does not belong to that set, so this is contradicting to each other. So phi2 belongs to Bj for infinitely many j's. For some, sorry. Yeah, because this was the assumption. The assumption was that for all j, this is not the case. We have now found a contradiction, so it means that there is a j for which this is not true. Therefore, for some j. Now we have to get to a next argument without loss of generality. Let j be the smallest index such that phi2 belongs to Bj. So it's starting from 0, the first index where phi2 is included. For all the intermediate ones, it's not included. Then the induction hypothesis for all the positions up to j yields that phi1 belongs to Bi and phi1 until phi2 belongs to Bi. No, for all these i's. Now applying the induction hypothesis, results in aj plus 1 satisfying phi2. Yeah, because we have phi2 in Bj. So from that, applying the induction hypothesis to that, we get this. And no, so maybe I do this with a color. So from this, I get this. And from this, I get that ai plus 1 satisfies phi1. So this is the green part. And this holds for all I less than j. Thus, a0, a1, etc. satisfies phi1 until phi2. And this is what we needed to prove. So again, in this part of the proof, you see the use of the definition of the acceptance conditions. Yeah, in particular here, you see that here we use the definition of these acceptance conditions, which is crucial to get the correctness of this proof. Good. I spent so much time on this proof because I think this is the key to model checking of LTL, and to my belief, you should understand why this actually is correct. And mentioned already that in the literature there are many different other algorithms being published. Actually, it's still a subject for research to get smaller and smaller and smaller Büchi automata, but the algorithms are typically much more complicated. The definition, like here, doesn't fit on one slide anymore, and the correctness proofs are accordingly much more complicated. And you see that even for this case, if you do this rigorously, it takes you quite a bit of effort to do this. Good. The last part I would like to spend on the complexity of the algorithm. And then in the next lecture, I'm going to show you that actually the LTL model checking is p-space complete. And that means that the exponential blow-up that we get in this NBA is unavoidable. So what's the complexity of the procedure we have seen? We go from an LTL formula, we negate it, and then construct the Büchi automaton for its negation. So this is what we just have proven. And this was the procedure we were following. Yeah, the definition transformed the LTL formula phi into a GNBA. And then, and this is the construction you have been confronted with in some of the earlier lectures, that you can convert any generalized Büchi automaton into an equivalent non-deterministic Büchi automaton. Maybe you happen, if this has k accept sets, what you do, you just copy. You make k copies and then you cycle around. And that basically was the main construction. So what's the complexity? Now this NBA, right? The size of this thing is something like the size of the GNBA times the number of accept sets. Why do we get this number of accept sets? This is because the copying. If the number of accept sets here is 8, we make 8 copies, and that's why this automaton is 8 times the size of the GNBA. Good, so this is the number of accept sets, and this is also good to know. The number of accept sets is at most the size of the formula. Why is this? Well, this is the fact because for every until formula, like here, right, f sub phi 1 until phi 2, we have an accept set. How many until subformulas can a formula have? Yeah, only linearly many. Yeah. So therefore, this cardinality is at most the size of the formula. Good. So that means we take the size of this automaton is actually 2 to the power the closure of phi. Why do I get the 2 to the power of the closure of phi? Well, we take the closure, which were the subsets, which were the subformulas, and then we take elementary sets. So we take subsets of the closure. This was already pointed out in the previous lecture. How many subsets can you take? 2 to the power the cardinality of the closure. So the blow-up is in the number of states. Yeah? So this is the size of this automaton. And that means that the size of the NBA is at most something at 2 to the power this thing, yeah, times the number of accept sets, which is in the worst case in the length of the formula. Yeah? So this is the size of the automaton that our algorithm provides. Good. So it's exponential in the size of the formula. Good. So we can make some remarks about the size of NBA. Actually, it's typically unnecessarily complicated. I already mentioned the algorithm I showed you is the one originally by Volpaire and Vardy. If you use tools nowadays to do the model checking, spin is one of those tools, then actually you will figure out that the Büchi automata they generate are much smaller than the ones we get from this algorithm. But as I mentioned before, proving the complexity of those algorithms is much harder. I don't know at the top of my head how many wrong algorithms have been published, but quite a few, yeah, where you reduce too much. So if you, for instance, take this NBA, next A, if I would ask you, can you give me an NBA for next A, you would construct something like, well, in the initial state anything can happen, but in the next state A should happen, and that's it. So this would be the NBA you would come up with. The algorithm, if you apply it step by step, and actually this is one of the examples in my slides, takes 4 states and 8 edges. So much more complicated than, let's say, this structure. Also this, A until B. This was another example which is in the slides, but I skipped this here for the moment. This would be something like A holds, until at some point B holds, and then, yeah, no matter what happens, you stay in the except set. So it's 2 states. The construction, if you apply the algorithm literally, gives you 5 states and 20 edges. Good. But there exist worst case formulas. So there are formulas for which this exponential blow up is unavoidable. So there exists actually a family of formulas. So phi n simply means it's a family of formula where the index or the subscript n is something saying about the size of the formula. So the size of phi n is polynomial in n. I will show an example in a minute. But I will argue that every NBA for such a formula has at least exponentially many states. Okay, so this shows you that the blow up by means of an example is unavoidable. So this is an LT property that has no small non-deterministic Büchi automaton. So the family of properties we are considering is written down as follows. So E of n, so I just write it down as a property, as an LT property. So this is a set of traces, right? It's the set of all infinite words of the following form. You have some prefix of size n, then this same prefix is repeated, and then something arbitrary. Okay, what is the key point here is the repetition of the first prefix. Good, so this is of the form xx, x is the prefix of length n, and that's repeated, and then something which happens afterwards which is actually arbitrary. So the LTL formula that corresponds to this property looks something like this. So phi n is a conjunction over all atomic propositions, AP, of some length, and here is this length n again, so n again is this length of the prefix, such that if there is an A at position I, if and only if n positions later, there is an A as well. Now this, I hope you see, this models the repetition. Yeah? And as you do this for all I, it really tells you that if there is, let's say, a symbol in this A2, then at n positions later, which is exactly here, this symbol, for instance small a, needs also to be in this set. Yeah? And because you do this for all I, you really say it repeats. Now this is of course a hypothetical case. I'm not claiming that this is a formula that you easily let's it. Of course this is polynomial in the length of n. No, I mean this is a constant length. Now you have this is a conjunction over n. Well, and this is also still linear over the number of atomic propositions, so you get something which is polynomial in the size of n. Good. Now let's look at the Büchi automaton you need for these words. What's the hard part? You need some kind of memory, right? Because you need to encode somewhere in the automaton that if this is the prefix, then you first have to see exactly the same prefix again before you can do anything else. And that's the key point. So let's take a very simple example, n equals 1. So I have a word which is simply of the form AA something. Good. If I just take a set of atomic propositions being a singleton, A, then the automaton looks as follows. So there are 2 possibilities initially. Either I have this input symbol, this set A contains an A, or it does not. Okay? Now here in that state, I have to repeat the same pattern as I have seen before. So if the incoming edge is labeled with A, its outgoing edge also has to be labeled with A. Yeah? And from there on, I can accept anything, because then I can accept those B's, which is the self-cycle in the accept state. Now, the automaton is symmetric, so here the same, but not A and not A. Good. Okay, this is the LTL formula A if and only if next A. This is if you expand the set of atomic propositions. So again, n equals 1, so I just have AA, but now I have a set of atomic propositions AP, and now I have to distinguish between all possible A's there. So what are all the possible subsets of AB? Well, they're 2 to the power 2, so I get 4 different outcomes, A and B, A and not B, not A and B, and not A and B. In those intermediate states, there is my memory, so to speak. So if the prefix was A and B before, I have only an outgoing edge with A and B. And the same for all the other states. Good. What happens if we, and this is the formula, A if and only if next A, and B if and only if next B. Now let's expand n a bit. So again, I restrict myself to a single atomic proposition, but n equals 2. So now I look at the words A1, A2, followed by A1, A2, followed by something. Now my automaton has to, first we have to have all the possibilities A1, A2, so I have something of the form A, and then I can choose between A or not A, or I can have not A, and then I have A and not A. Now the positions here, that's exactly their subscript. 1, 1 means I have reached that state by first doing an A and then reaching an A, and then doing an A. So what should I do? I do first an A, which is the correct copy of this A, and then I do, here I have this A, and this is the copy of that A. Yeah, so here you see A and not A, followed by A and not A, and so forth. I think you get the idea. Yeah? I have to encode all possibilities. Now there are exponentially many possibilities, so your automaton will be exponentially large. The formula was polynomial, but the automaton is exponentially. This is the LTL formula. A if and only if next A, so 2 positions later A, and if in the next position, n equals 2, then 3 positions later, I mean 2 positions later after this position, which means now 3 times next A holds. Yeah. Good. The general case has 2 to the power n, at least 2 to the power n states, and the point is that basically here you get 2 to the power n states because you have to basically encode all the histories. What has been the prefix until reaching that state, and there are 2 to the power n of those histories. Is this blow up? Now you might argue, okay, don't use automata. Yeah? If this is the problem, why are you so keen on using automata? Yeah, of course you can try to use something else. So what we're going to see in the next lecture, next Tuesday, we're going to talk about Turing machines, and we're going to show that the reduction of LTL to Turing machines leads you to a proof that this actually LTL model checking is p-space complete. So you cannot avoid this exponential blow-up. How clever you can be on every Sunday afternoon, this will not work. And that's what I'm going to show next Tuesday. I wish you a nice weekend and a nice Sunday when you're going to beat the Mexicans.